Yeah, there are a lot of people outside having their breakfast. Yeah, we'll start on time. Yeah. Okay, so welcome to the third day's plenary session. We have four speakers today. The first one, Anuprita More, and she'll be talking about gravitational lensing in the LSST era.
Good morning, everyone. I'm going to talk about gravitational lensing in the LSST era. So in strong gravitational lensing, we can see multiple images of the distant source galaxy due to the gravitational potential of an intervening massive object like a lensing galaxy or a group of galaxies. On the sky, you can see images like this, where the multiple lensed images are surrounding the intervening galaxy, and the image separation between this gives you a sense of the total mass that is enclosed within this galaxy. This image separation, in this case, you see almost like a ring that is formed. So this is called the Einstein ring, and the radius of this ring is called the Einstein radius. So what lensing allows us to measure is the total mass within this Einstein ring, which we can measure via the Einstein radius. Another very important thing is that the mass distribution of this intervening massive object plays a critical role because it dictates the kind of image configuration you will see and also the number of images that you will see of the distant source. The main lensing observables are the positions of the images, the magnifications of the different images, as well as time delays. So the time delays are basically, they arise because the multiple images that you see, the light rays coming from these multiple images, they take different geometric paths, and they also experience different gravitational potential. And so the images that you're seeing, they arrive at different times at the observer, so there is this time delays that one can observe. So in general, lensing can be used for many different applications. So firstly, lensing can be used for constraining the dark matter distribution, as I was saying. So let's look at this example over here. There is a very massive cluster, and you can see lots of bright galaxies here. You can see lots of bright galaxies, but if you look at the profile of these multiple images, these giant arcs that you can see, it's more or less spherical, and that clearly indicates the enclosed matter distribution is kind of spherical, which is coming through this invisible dark matter that's present there. And so the other factor is the kind of giant arcs, distorted arcs that are formed from these very distant and faint galaxies. There is a zoom of this section here, and you can see how detailed this image looks like, where you can see these clumps and knots of star formation in this very distant galaxy. So what you get here is like a magnification factor of 30 or 40 in this kind of system. So you can use lensing as a cosmic telescope to study these distant faint sources. Additionally, with the time delays of some lensed transients or variable sources, you can measure the cosmological parameters like the Hubble constant and so on, because these time delays, they depend on the angular diameter distances to your lens and the background source. So what I'm showing here are images of a strong lensing cluster, and here I have circled these lensed supernova that went off in this particular cluster. Luckily, this system not only showed one lensed supernova, but also after a few years, there was another supernova that went off in the system. And with the help of these kind of lensed supernovae or lensed transients in general, we can, if we measure the time delays very well, then we can get constraints on cosmological parameters. Additionally, because lensing allows us to see the same event multiple times, you can also get a good understanding of the progenitors of these supernovae, or learn the physics of the supernovae, because we can predict when the next images will occur. So strong lensing is very rare. And we need large and deep imaging surveys to discover these strong lenses. What I'm showing here is just a plot as a function of the area and the depth of various surveys. So you can see lots of surveys which are plotted over here. I want to point out the Hyper SupremCam survey on the Subaru telescope, which falls in this 1000 square degree kind of imaging survey. In that sort of zone, the HSC survey is the deepest compared to all of them. And this is going to be superseded by LSST in the next generation of surveys, going to the 10,000 square degree regime. So the HSC survey is a precursor to the LSST, and it's an excellent test bed for different science cases that we expect to do with Rubin LSST. So most of the work that I'm going to present in this talk is actually done with the HSC survey, and then also how we can do this better with Rubin LSST. So let me say a few words on Rubin LSST. So the Rubin telescope is located in Chile, and it's named after Vera Rubin, who gave us the first observational evidence of dark matter. And this, the survey that is going to be conducted with this Rubin telescope is called the Legacy Survey of Space-Time, LSST. It's a 10-year-long survey which is going to span nearly half of the sky, covering 18,000 square degrees, and it's going to take repeated images of the sky such that you will form a movie of this half of the sky, and you'll be able to study the transients, variable sources, and many other things with this survey. In this survey, we're going to record some 37 billion stars and galaxies. There's going to be worldwide alerts released every night. We expect something like 10 million alerts happening every night, producing 20 terabytes of data. Within the collaboration, there's going to be annual data release, which will give access to many more data products, including the static sources and the coads that will come from these data releases. The data is also going to be fully public after the 2 years from the data release. So the current status of the Rubin LSST is that the science validation survey is over, and it is covered something like 1000 square degree up to half of the year 1 depth. We're expecting a data release sometime in September 2026. Next, we are planning the year 1 survey, which is going to start pretty soon, and the data release for that is going to be sometime in late 2027 or early 2028. The LSST science community has self-assembled into different science collaborations, which are listed over here. They span different science cases, science goals. There are 8 of these science collaborations. They are completely autonomous and independent. They have their own code of conduct and policies and so on. I'm involved in a few different collaborations, but primarily in the strong lensing science collaboration. So let me say a few words about the strong lensing science collaboration, which is SLSC. I'm one of the co-chairs of the SLSC, and we are conducting multiple collaboration-wide activities in preparation for dealing with the LSST data. Some of the activities are as follows. So we are conducting mock data challenges that involves generating different types of training data sets to test lens search pipelines and lens modeling pipelines for sources like lensed galaxies, lensed AGNs, and also lens transient sources. We are also developing a candidate central database which will hold all the candidates coming from different lens search pipelines. We are also working on a tailored image cutout server which will serve all the needs of the various search or analysis or modeling pipelines that will need to analyze the standard coads. Furthermore, we are also coordinating with Space Warps, which is a citizen science project for discovering strong lenses. And also assigning visual ranks, grades to the kind of lens candidates that we'll find. I am one of the co-PIs of the Space Warps project. Furthermore, we are also doing coordinated follow-up activities which will help optimize the different follow-up that will be conducted of the candidates that are found from the LSST, so that we can help share these resources among the different SLSC members. The website is over here, and so you can take a look at all the various activities and related projects and so on. So in the next few slides, I'm going to talk about the different science that I've been doing with the HSC survey, as well as some of the ongoing activities within the SLSC, the Rubin LSST collaboration. So first, focusing on the galaxy scale lenses. So some of the interesting things that we can do with the galaxy scale lens samples is, for example, looking at the stellar mass IMF. So there are various questions regarding the stellar mass IMF, like is this universal? Does the stellar mass IMF depend on the different types of the host galaxies? Are these radially going, as you go from radially outwards to within a galaxy, is it constant, or is there some sort of gradients? We can try to understand these kind of questions using strong lens systems. So the rough idea is that at the location of the Einstein radius, you get a very accurate measurement of the mass coming from the strong lensing. So that's shown by this line here. And with the weak lensing, we have a very good idea of the overall mass distribution, especially in the outskirts. And so if we take that and extrapolate it towards the inner regions, then we have some sense of the mass in the inner regions. And if you just take a difference between the strong lensing mass and this weak lensing mass, then what you essentially get is the mass that's there in the baryonic component, or the M star, as shown over here. So this is one measurement, and the other measurement of the M star, the stellar mass, can come from the stellar population synthesis models. And so if you take a ratio of this is given by this alpha IMF, which is this mismatch parameter, and we have tried to measure this from a sample of strong lenses found from the HSC survey, which we call the Sugoi sample. So this is the Sugoi G sample. So with this sample of a dozen or 2 dozens of strong lenses, we have tried to measure this mismatch parameter following a hierarchical inference model. And here what we are showing are the constraints on the mean and the sigma of this IMF the alpha IMF distribution. And what we are finding is that this is more or less consistent with the Chabrier IMF, which is somewhat in tension with other studies which prefer Stolpeter IMF. One important thing to note here is that there is some sort of degeneracy between this inner slope of the dark matter profile and the choice of the IMF, the current sample that we have is fairly limited, and this can be further improved if we get much larger samples, which is possible with surveys like the Rubin LSST and Euclid. So this can be further improved. And so some of the other things that I wanted to point out, that we are working towards developing better and faster algorithms for searching lenses. And so here are results from one of this fairly recent work where we have created these realistic samples of simulated lenses and non-lenses, and we have developed a neural network which can find these lens systems with fairly good accuracy. Here's a histogram of the resulting lens population that is found, and the redshift distribution is fairly similar to what we expect. This gallery shows some of the most promising grade A lens systems from this sample. We have found over 300 lenses from this particular work, and then this is also in combination with many other such efforts that are happening within the collaboration. Another thing that we are trying to put efforts toward are developing methods that will allow us to not only search for lenses but also model them using these neural networks, because that will allow us to perform this modeling very fast as well as giving us sufficient accuracy. So just to give you a sense of some numbers, the typical mass modeling that used to be done conventionally for individual systems, that involves like the conventional MCMC methods which takes several tens of hours for one system. And in comparison, if we try to develop methods based on neural networks, then they can do the model parameter predictions in the matter of few seconds to few minutes. And so with this project, we developed this neural network which could predict the some of the parameters. For example, here we are looking at the true Einstein radius versus the predicted Einstein radius, and these two parameters, they reflect the ellipticity of the lens mass distribution. And as you can see that this network is doing fairly good job. We have also done some systematic comparison with a handful of lenses which were available and studied by different teams in detail. And you can see there is reasonable agreement for the Einstein radius, but we are still somewhat struggling with additional parameters like the Einstein, like the ellipticity and so on. Another activity then, extending this to the SLSC and trying to do this more rigorously and preparing for the LSST. Within the SLSC, we are conducting this mock data challenge. So this is called the Rubin Static Strong Lensing Data Challenge, and the goal here is to develop and benchmark different pipelines that can be that can have sufficiently good performance and are prepared for handling the LSST data. So this challenge involves both for searching and for modeling lenses, and in this case we have generated these two classes of lenses and non-lenses, and the type of data sets that we have worked on are both pure mock LSST data as well as taking the existing HSC data and then modifying it, adapting it to the LSST like LSST-like design or the image quality and so on, and create this kind of adapted data set which includes real objects from HSC survey. So we have this combined kind of samples in our data sets. The decomposition of the different training and the test and other samples is given over here. In this plot, I'm showing the distributions of the different parameters that went into generating the mock lenses, shown for the two different algorithms that are used in this work. The challenge was open until October 2025, after which we have stopped the challenge officially, and now then assembling all the results and doing further analysis on the data. So in total, we have more than 20 teams who have participated in searching for the searching part of the doing the lens searches in this challenge, and then there are 5 teams who have participated for the lens modeling part. And in addition to the networks and the results that we have obtained from the different teams, we have also actually developed our own ensemble networks, which will take the trained networks from these different teams and perform another few layers of training of some sort of neural network, which will then give us the combined results coming from these different networks. And so these ensemble networks are also being analyzed within our team, and some of the results are shown over here. They are fairly preliminary. So on the left hand side, we are showing the results from the lens modeling. On the x-axis, we have the expected parameters like the Einstein radius, ellipticity, magnitude of the background source, size of the background source, and so on, and the y-axis shows the predictions. The columns are for different teams. And on the right hand side, we have the typical the ROC curves, which allows us to evaluate how well the networks are performing, and these different panels show results from different teams. So more work is going on in this direction, and so you will hear soon the entire results that we have obtained. This website also gives you details of this challenge. So now moving on to the other area, which is the groups and cluster scale lenses. So here I am interested in looking at the mass distribution. So for example, talking about the galaxy group scales, these are relatively less well studied. There is interplay between baryons and dark matter in these systems, so they are fairly complicated. But the good thing is that galaxy groups are much more abundant than clusters, and so what we have done is that we have tried to look at the image separation distribution. So if we have a large sample of lenses and if we look at the image separations or the Einstein radii of this sample and look at the distribution of these image separations, then we can try to get constraints on the mass distributions. So what we are showing here, for example, with the magenta points, these are the observed data sets. And we are comparing these with 3 different models for the mass distribution, the blue, the red and the black, which are different theoretical models. And what we find is that the black solid curve, which is the composite model for the mass distribution, trying to capture the baryonic effects in the central regions and and assuming that the dark matter is more dominant in the outer regions. So this kind of composite model is what is shown with this black curve, and that seems to fit this image separation distribution fairly well. We have demonstrated this with the sample of 120 lenses found from the CFHT legacy survey. We have also then tried to further improve this by testing additional models for the dark matter. So if the dark matter within the inner regions, if it is not NFW, but if the slope of this dark matter profile is changing because of the presence of the baryons, then that sort of effect is shown by this dashed dotted curve, and you can see that how it affects the slope of this distribution. But since this effect is so small, we need to have very large samples so that we can get good statistical constraints, as well as very accurate measurements of these image separation from each of these lenses is required. And this is where fast methods for modeling accurately and searching for these systems comes in. And so if we can do this with larger samples, then we can get much better constraints. So the plan is to do this with the current sample of HSC lenses. This is the Sugoi C sample, and then in the near future, we also want to make some predictions and tests for the Rubin elasticity data. So you can also see a poster by Khushi Lalit, who's working on this project. So in that for that goal, we have also been looking at searching for these groups and cluster scale lenses, and this is just pointing out one of the results from the HSC survey collaboration, where we worked with different sample of cluster catalogs and selected some 40,000 clusters on which we then performed visual inspection to select some top 230 promising groups and cluster scale lenses. We have also done spectroscopic confirmation for a handful of them. You can see the redshift distributions and the arc radii or the image separation distributions for the system here. And so Khushi will be making use of some of these samples to further improve the constraints that we got in the previous work. So let me talk about now the lens transients. As I was mentioning earlier, that the lens transients, for example, supernovae and kilonovae, these can be extremely useful not only to do cosmology but also to learn more about these sources themselves. So to this end, we have been looking at some fast methods that will allow us to rapidly distinguish the supernovae. So let me start with supernovae of type 1a. So distinguish the supernovae of type 1a from some other kinds of transients. So the idea here is that if we have the type 1a supernovae, which are standard candles, then at higher redshifts they look dimmer and redder compared to the lower redshifts. But if these type 1a supernovae are lensed, then they will still look redder, but they will look much brighter. So they will end up in this part of the parameter space. And so in Quimby et al, we had developed this or proposed this method of using this color magnitude diagram as a means of quickly identifying lensed supernovae of type 1a. And this work was then further extended using systematic samples of lensed and unlensed supernovae of different kinds, and this work was done by Prajakta Mane, and you can see a poster by her in this conference. And so what we are showing here is that we are able to, with this method, we are able to distinguish the green versus the black, which is the lensed versus unlensed population, fairly well. Furthermore, we are also extending this analysis to go closer to the data. The electromagnetic counterpart, and these kind of systems are expected to be discovered with the Rubin LSST, and so we have been doing some studies to understand how to spot these kilonovae, whether they are lensed or not lensed, how to spot these kilonovae and how to distinguish them compared to the other types of sources, other types of transients like supernovae, type 1 and so on. So here we are looking at the color evolution. Here we are color evolution shown for different redshifts. We also looked at different colors, but it is showing here for R minus I. And the red population is the kilonovae population, which is detectable in the LSST. And then the other colors show the different types of transients. What we have come up with is that if we look at this color evolution at the peak of the light curve versus the peak plus 3 days, we find that we can easily distinguish the kilonovae from the type 1 supernovae, because the kilonovae are much more rapidly evolving compared to the supernovae. So there is a poster by Anindya Ganguly on this work, so please refer to that. Want to also point out that we also looked at the lensed kilonovae population, and here we are showing the lensing magnification as a function of redshift, and all these points here, they are the lensed population that we have generated. The curves here, they refer to the GW170817 like kilonova, and anything, if the kilonova happens to be on this side of this curve, then it will be detectable with the Rubin LSST. And what we are finding is that the typical population that we are finding, if we can actually observe much deeper, so something like 180 seconds or deeper exposures, if we can get from the Rubin telescope, then we can find some of these lensed kilonovae. I just want to mention very quickly about the space warps and the citizen science efforts. So, like I mentioned, the Space Warp project is a citizen science project for finding gravitational lenses. This is unlike many other citizen science projects, because in this work we are actually using this as a supervised learning framework, where we are injecting training data sets, and we are doing training on the human classifications. And so this the candidates that we actually get from the space warps are essentially candidates which have probabilities for something, whether the images have lenses in them or not. So we can actually use this kind of sample to do statistical studies, and so this is what we have done in the past. I'm here showing some results from the HSE survey, and more recently we have been also doing searches with the Euclid survey, and here is a gallery of some lenses that have been found from Space Warps Euclid. Over 500 new lenses from the the Euclid Q1, what is called the Euclid Q1 survey, and now the full data release 1 is being analyzed. So the Space Warps is currently live. You can go to the Space Warps website and you can join, and you can help us with the classifications. In the near future, we are also going to do Space Warps with LSST, and I would like to stop here with the summary. Thank you.
Excellent. She's 49 seconds early. So you can have many questions. Yeah.
You know, there are particle physics models of the early universe with cosmic strings. Cosmic strings,
Yeah.
which have very distinctive gravitational lensing signature. Is there any plan to have a dedicated search for those?
So within the strong lensing science collaboration, at least no one is really right now looking into the cosmic strings related effects. Yeah, I think there are some people in the astronomy community who are interested in looking at cosmic strings, but nothing that I have seen within the SLSC.
No more questions? Yeah.
So you do supernova search in the difference images in different bands. So is it done separately or you also combine the data from different bands?
We combine the information from the different bands. We analyze it together. So we will, some of the detection criteria will be on the basis of whether we have found a particular candidate in multiple bands, at least in some n epochs. So, yeah.
But it will also depend on how the supernova behaves at different bands, right?
Yes, yes.
That is folded into the...
that information is used, yes.
Questions? Yes.
You mentioned that supernovae that are gravitationally lensed will be found very likely by LSST. From your simulation, your work, and past discoveries, do you have a rough idea of how many we may expect to find, ballpark?
Yeah, the expected numbers are something like hundreds, in the order of hundreds for the type 1A supernovae.
Over the 10-year survey or per year?
Over the, I think the 10-year survey. Yeah.
That's exciting. Thank you.
Yeah.
If there are no more questions, let's thank the speaker once again. Next speaker is Ananda Narayanan, and he will be speaking about probing the cosmic baryon cycle with quasar absorption line spectroscopy.
Good morning, everyone. At the outset, I would like to thank the Scientific Organizing Committee for extending this invitation, and also to the local organizing committee for all the wonderful hospitality that has been extended over the last several days. I will talk about some of the observational strategies that have been deployed over the last 2 to 3 decades to detect substantial baryon reservoirs, particularly in the low redshift universe, redshifts less than 1, where this work is challenging for a number of reasons, as I will explain. And I'll restrict most of my discussions to the quasar absorption line spectroscopy as the observational tool for finding these baryons. But I will also touch upon some of the complementary methods that have been used and the kind of results that have come out from those. And I will put some of the work that we have been doing at IIST, primarily led by students of IIST, along with. So, one of the very well measured cosmological quantities is the cosmic baryon density, omega b. There are multiple lines of evidences that allow us to constrain this value of omega b to less than 1% accuracy. One is, of course, the angular power spectrum of the CMB, where the ratio of the peaks the odd and even peaks put a very tight constraint on what is the total inventory of baryons in the universe, and the other is the predictions made by the light elements the predictions made by the Big Bang nucleosynthesis on the relative abundance of light elements in the universe. So that is another constraint on the value of omega b. So this quantity is pretty well determined. Now what is really not known where are these baryons present at different epochs in the history of the universe? What are the astrophysical systems that harbor these baryons from the high redshift to the present? So cosmological simulations help us to get a very nice overview of the baryon inventories. For example, if you take a representative volume of the universe at the high redshift, most of the baryons reside in the intergalactic medium, the space that separates galaxies. At the very high redshifts, galaxies are still forming, so these baryons are largely present in the intergalactic medium. And they are present in this cool photoionized phase. So when I say cool, I mean temperatures of 10,000 Kelvin and photoionized. That is where most of the baryons are present, and since the universe is much denser in the past, for a given mild overdensity region, there is still substantial amounts of neutral hydrogen that is present, which leads to the production of this Lyman alpha forest of absorption. So what you see here is a spectrum of a quasar, and let's say that this quasar is at some high redshift and the light is passing through the universe. So this is the Lyman alpha emission from the quasar, and blueward of the Lyman alpha emission, when we observe these high redshift quasars, we see a large amount of neutral hydrogen that is producing this forest of absorption, which is called the Lyman alpha forest. So at high redshift, the baryon census is fairly complete because most of the baryons are present in this cool photoionized IgM traced by the Lyman alpha forest. Now, with the passage of time, a lot of interesting things happen to these baryons, and the two most important things that drive these baryons out of this cool photoionized IgM is, one is of course the expansion of the universe, so therefore the amount of neutral hydrogen present in a given overdensity comes down as space stretches. So several of these low column density IgM tracers go below the detection sensitivity of observations. The other more important factor is the formation of the large scale structures. So when we do the similar Lyman alpha forest search at the lower redshift universe, where you need ultraviolet spectroscopy capabilities, we find that the Lyman alpha forest has indeed thinned down. Instead of this forest of absorption, you have these isolated H1 clouds that are producing Lyman alpha features in the spectrum of quasars. So the Lyman alpha forest does thin down, and if one does a statistical survey, one finds that the amount of baryons that are entrapped within this cool photoionized IgM is roughly about 30%. So there has been a reduction in the amount of baryons that is present in the cool photoionized phase of the IgM, and one would expect in a very simple manner that the remaining baryons should have flown into galaxies as a part of structure formation. But as it turns out, that is not the case. One can, at the low redshift, galaxy surveys are fairly complete. One can detect the galaxy luminosity functions to very faint luminosities. So there are several galaxy redshift surveys that one can use, and from these galaxy redshift surveys we get the galaxy luminosity in the optical and infrared, where we get the galaxy luminosity functions, and using some stellar population synthesis models, and also from some converting these stellar population synthesis model estimates from using some mass to light ratios, you can convert them into mass luminosity functions, and from there one can get an estimate of how much of baryons are present inside galaxies in the form of stars. Similarly, you can complement it with H1 observations and molecular gas observations in the low redshift universe, which tell us how much of gas is present in the interstellar medium within galaxies. So you add all of this up, you get a total estimate of how much baryons are present within galaxies in the form of collapsed structures, stars and interstellar gas, and that value turns out to be about 10 to 15%. So this means that there is a substantial fraction of the baryons are neither present in the cool photoionized phases of the IgM, nor are they present in galaxies, and this has been the kind of the impetus for this problem called the missing baryons problem, which is now largely solved. So simulations again, tell us where to look for these baryons in the low redshift universe. So this is actually a graphical representation of where the baryons are present at different epochs in the history of the universe. So as you can see here, As you can see here, at the higher redshift, most of the baryons are in the Lyman alpha forest, and with the passage of time, the amount of baryons that are present inside galaxies is increasing starting from a very low percentage out to about 10 to 15%. So even after 10 billion years of the evolution of the history, only about 10 to 15% of the baryons have actually flown into galaxies, which means that in a way we can say that galaxy formation has been a relatively inefficient process, and the cool photoionized phase also comes down, but what one sees is the emergence of what is known as the warm hot intergalactic medium. So what happens here is that as gas which was present in the IgM filaments, IgM, it actually flows into the dark matter potentials where galaxies, galaxy groups and galaxy clusters are forming. This gas exceeds supersonic speeds, or this gas is moving in supersonic speeds, which leads to astrophysical shocks, and these shocks heat up these baryons to temperatures of 100,000 to 10 million Kelvin or so. So this is a new phase that emerges as a result of structure formation which was not present in the high redshift universe. So therefore, if you just look at this map, you can see that the low redshift universe is much more complex. You have an admixture of several different density temperature phases, and a substantial fraction of the so-called missing baryons are present in this gas phase with very high temperatures, warm corresponding to 10 to the 5 Kelvin and hot corresponding to 10 to the 7 Kelvin. And these warm hot gas phases are to be found in the regions close to galaxies as well as in the intergalactic filaments where the cool photoionized Lyman alpha clouds also exist. So these are the typical densities and temperature where you expect the WIM, and the WIM is the warm hot intergalactic medium, and the hot gases surrounding galaxies. And so how does one go about finding them? At these temperatures of 100,000 to 10 million Kelvin,
most of the hydrogen is collisionally ionized. So one cannot use hydrogen as a tracer, atomic hydrogen as a tracer of this warm hot phase. One has to rely on highly ionized metals. So what this graph is showing is the temperature density kind of phase diagram, and what are the key ions which are diagnostic of these temperature density phases. Okay, and I want to draw your attention especially to the left end of this, where you see temperatures of 10 to the 5 to 10 to the 6 to 10 to the 7 Kelvin, and that is the regime where a lot of these baryons are lurking in the low redshift universe. And in order to probe this, since we do not have access to atomic hydrogen, we have to rely on highly ionized metals like oxygen 6, neon 8, magnesium 10, sodium 9, etc. And all these ions have electronic transitions in the far ultraviolet part of the electromagnetic spectrum. So therefore, instruments that are optimized to look at the universe at far UV and UV have been used for this purpose, primarily spectrographs on board HST, the cosmic origin spectrograph, and the STIS spectrograph have been used for this work. And in addition to UV absorption line spectroscopy, as I mentioned, X-ray and X-ray, both absorption spectroscopy in X-ray and also X-ray in emission, and FRBs have also been used. I will briefly talk about results from the complementary techniques also, but will largely focus on quasar absorption line studies. So this is a slightly crowded slide, but I want to put together a lot of things in one slide. From our side, we have been trying to go after these exotic neon 8, oxygen 6 absorption lines that are tracers of the WIM and hot gas associated with CGM. So these are from different papers led by students of IIST. So what one sees over here, in each panel what one is seeing is a small part of a quasar spectra, a line of sight that is piercing through the low redshift universe, and at some low redshift there is a parcel of gas that is producing an absorption, and that absorption feature is stacked one after the other. So you have atomic hydrogen, Lyman alpha, Lyman beta, higher order Lyman lines present. In addition to that, at that same velocity, we also have oxygen 6 absorption. So this is what typically an oxygen 6 absorption in the low redshift would look like. And once we have information like this, one can do detailed ionization modeling by measuring the strength of these absorption features, comparing the strength of individual metal absorbers against individual metal ions against each other, and come up with estimates for the physical conditions that prevail in the gas that is producing this absorption. So this is one example. Here is another example where we have shown neon 8 detections. As you can see, the neon 8 detections are very faint.
One of the reasons being that neon is not as abundant as oxygen. Oxygen is the third most abundant element in the universe, whereas neon is the fifth. So the cosmic abundance of neon is much lesser, and therefore we always see it as a very weak feature, which means that you need very high signal to noise spectra in the far ultraviolet wavelength. And usually the neonate detections are very well supported by complementary detections from oxygen 6. So the neonate plus oxygen 6 allow us to firmly constrain the temperature in that gas phase, which is often reminiscent of the kind of temperatures that exist in WIM or in the hot CGM. Some more examples are given here. Now there is also a way to constrain the amount of baryons by looking at just thermally broad hydrogen in the IGM. So all of these are towards the right, and all of these are thermally broadened hydrogen absorption profiles, and that also allows, so these are called broad Lyman alpha absorbers. That is also used for determining the amount of baryons present. There are a lot of details that one has to take care of. For example, the metallicity estimates are crucial for determining how much of baryons is present in each of these gas phases, and though there are uncertainties associated with that, I just want to mention that. So there are through statistical surveys of neonate, oxygen 6, etc. Now we have a fairly good estimate of what is the baryon fraction in each of these phases. Now moving on, there are complementary methods for finding this warm hot gas phase. So in this one slide I have put together all the major methods that have yielded some detections. One is of course X-ray absorption spectroscopy. So here is an important landmark study by Nicastro et al, and they have put out a few papers along similar lines, where they have looked at very bright X-ray blazars as background sources to detect absorption in X-ray. So this is oxygen 7 helium-like absorption happening here at X-ray wavelengths, and from this and using some very careful analysis, they have tried to argue that this absorption is not arising in the individual halo of a galaxy, but is rather arising from the hot phase of the intergalactic medium, the WIM. Here is another example, again Chandra XMM and Chandra and XMM Newton observation. So these kind of studies are happening, but you can see the challenges involved here. These X-ray absorption lines are very weak. They are few milliangstroms in strength, and one has to, they are seen at very low contrast with respect to the continuum. So one needs very bright X-ray background sources and very high sensitive observations to execute this. So you are operating at the kind of the sensitivity limit of current X-ray facilities. So that's about X-rays, detecting WIM in X-ray absorption. There's also been attempts to look at the WIM through the Sunyaev-Zeldovich effect. Now WIM by definition contains highly ionized gas, so there's a lot of free electrons present at large temperatures. The only challenge here is that the signal is very weak, so one has to go for a statistical stacking approach. Just to give an idea of what the strength of the signal is, if you the signal is going to depend on the electron density and also on the temperature. So if you compare the electron density and the temperature of a WIM filament with that of the hot intracluster core, then one would see that so one would see that the typical WIM filament has an electron density that is roughly 100 to 1000, factor of 100 to 1000 less than the hot intracluster core of galaxy clusters. The temperature is about a factor of 10 to 100 less. So you multiply those two, the electron pressure is going to be 3 to 4 orders or even 5 orders of magnitude less than what the Sunyaev-Zeldovich signal would be from the cluster core. So you are trying to pick out a very weak signal from the WIM filament superimposed on top of a much stronger case. So one has to go for a statistical approach, which is what de Graaf and others have done. They have looked at millions of galaxy pairs from the Sloan Digital Sky Survey, and they have taken these galaxy pairs, not galaxy clusters but individual galaxy pairs, which are separated by roughly about 6 megaparsec in the plane of the sky, and they have oriented them in such a way that it's all in a common reference frame, and they have stacked these together, the Planck and the ACT data for this. They have stacked this together, which gives the signal, the stacking signal is obtained, and then they carefully subtract out the circular Sunyaev-Zeldovich signal that is coming from the individual halos of those galaxies, so that what remains as a residual is a thermal Sunyaev-Zeldovich signal from the WIM filament that connects these galaxy pairs.
Okay, so this is a very hard work, but it has been done and it has yielded some detections. And finally, there is this amazing possibility of detecting BIM through FRBs. Jayant Roy had yesterday talked about this particular aspect on how fast radio burst, the dispersion measures can be used to determine baryons in the low redshift universe, and that has been the most successful among all the techniques. That has been the most successful. As more and more FRBs get localized, I am sure this work is going to progress forward. So now that the cosmic baryon problem is more or less resolved at the global cosmological scale through all these complementary techniques, the quasar absorption line technique and the Sunyi-Zeldovich effect and X-ray absorption, and the FRBs. Now that it is mostly solved, the question shifts to much more interesting topics like where are these baryons distributed, okay, and what kind of physical states do they occupy, and how do galactic scale processes like feedback from star formation, recycling, etc., how do they affect this baryon reservoirs which are part of this larger network. And what about metals? You know, you're talking about hydrogen. What happens to metals as this structure formation progresses? So I'll touch upon these points now. So if you look at the baryon fraction, which is the ratio of the baryon density to the total matter density, which is dominated by the dark matter densities, that value comes out to be roughly 16% in the universe. So when a dark matter halo therefore forms, and as this dark matter halo accretes matter, the gravity does not differentiate between dark matter and baryonic matter at some level. So therefore you expect that the dark matter halo should have a baryon to dark matter fraction that is roughly reminiscent of this cosmic baryon fraction, which is 16%. So every dark matter halo should have baryons to this amount. So when one does the observations, one finds out that there is a deficit. So what is plotted along the horizontal axis, or what is in the schematic diagram, what is along the horizontal axis is the combined galaxy stellar plus interstellar mass, that is gas baryons within galaxies, and this is the baryon fraction. You find that at all mass ranges, the amount of baryons which are present inside galaxies is less than what is expected of the cosmological ratio. This is about 16% is what the cosmological values, and it is much less. The deficit is a little less around L star galaxies. It is much more towards the low mass end and much more towards the high mass end, the discrepancy. At the low mass end, there is a discrepancy because correlated supernova events, for the case of dwarf galaxies, correlated supernova events inject a lot of energy and momentum into the ambient medium, which pushes the gas out. And since dwarf galaxies are existing in shallow dark matter potentials, most of this gas escapes out of the galaxy. So they were part of the galaxies formed with a similar baryon fraction as the cosmic value, but over time, due to star formation and the feedback processes, the baryons have been pushed out of these galaxies. At the high mass end, AGNs keep the halos of galaxies hot. So most of these baryons which are present in the extended envelope surrounding galaxies, they never cool and collapse into the galaxy. So that is the reason why there is a deficit. Okay, so one can observationally verify this picture. So what is shown here is how the neutral gas metallicity evolves over cosmic time. Okay, from the high redshift to the present universe, we see that the metal abundances are increasing inside galaxies. These are ISM metallicities. These are H1 metallicities associated with damp Lyman alpha absorbers seen along quasar and GRB sight lines. So you can see that there is a slow buildup of metals with time that is happening in the universe, and this is because stars are producing heavier elements which are being thrown back into the interstellar medium. Commensurate with this, one also sees when one studies intergalactic absorbers, metals present in the intergalactic medium traced with carbon-4 absorbers. So this is work that one of the former IIST students had done. You look at carbon-4 absorbers, low column density carbon-4 absorbers, which are tracers of diffuse gas most likely associated with the intergalactic medium. We find that the omega C4, the amount of carbon-4 that is present in the intergalactic medium, in other words, carbon-4 is a proxy for metals, the amount of metals present in the intergalactic medium is slowly increasing with time. The amount of metals that are present in outside of galaxies in the low redshift universe is an order of magnitude more than what is present at high redshifts. So this is happening. Abhijit Anand had yesterday a talk where he also talked about the same thing. And we can also look at galaxy cluster outskirts. Galaxy clusters, the gas associated with galaxy clusters are typically studied in X-rays when you want to detect the intra-cluster medium, but there is also large reservoirs of gas in the outer regions of clusters, in what is known as the circumcluster medium. So this is a study where we looked at lines of sight to background quasars that pass through the outskirts of galaxy clusters, and we found out that at the outskirts there are large reservoirs of neutral cool gas that is present, which is not traced by X-ray observations. So X-ray observations will not reveal you this gas. This gas also has substantial amount of metals present in them. So these are estimates of the amounts of metallicity that is present in the cluster outskirts. So this shows that cluster outskirts have large reservoirs of gas. Possibly these clusters are accreting material from the cosmic filament, and also there is tidal disruption that is happening, tidal interactions which are happening, which are displacing interstellar gas from inside galaxies to cluster outskirts. So these are very interesting environments to study the baryon cycle processes. Now, an allied problem or an allied issue with this displacement of baryons from galaxies into intergalactic spaces is also the displacement of metals. So metals at the low mass galaxy end, most of the metals that are produced by stars in the history of that galaxy, they are not to be found inside the galaxy, but most of those metals are deposited in the circumgalactic space. So if you do not observe the circumgalactic space, then you are missing out on a lot of these metals, and these metals are part of different processes. The galaxy accretes material from the intergalactic medium, and that is preferentially oriented towards the major axis of that galaxy, and outflows which happen from galaxies due to supernova events, that these are preferentially oriented along the major axis, which is the path of least resistance. So when you observe a galaxy, we expect to see evidences of accretion and outflows as a function of the azimuthal angle. So if you take the major axis of the galaxy, most of the accreting material is likely to be found along the projected major axis of those galaxies, and the outflowing metal rich material is likely to be found along the along the minor axis. So what we have done of late in the last several years is to use integral field unit spectroscopic data from the MUSE IFU on VLT along with HST cos spectroscopy to study inflowing and outflowing gas along quasar absorbers. For the paucity of time, I'll just go over some quick results. So we have looked at absorption systems where we find evidence for gas that is accreting along the major axis of galaxies, and the properties of this gas resemble those of cold accretion streams that are expected in the case of galaxies that are living in dense environments. Okay, so that is one example, and in that same environment we also find evidence for another case where gas is moving out of galaxy along the projected minor axis. This gas is metal rich and possibly is tracing outflow. So in one set of observations, we have found two examples of gas being accreted from the intergalactic medium and gas that is outflowing also through this technique. And this technique has been extended to several absorbers of late, mostly led by students, and in every case we find that the IFU data, the integral field unit spectroscopic data, is really helping us to understand the kinematics of the emitting gas associated with galaxy, and the quasar absorption line spectroscopy is providing information about the absorbing gas. So in one go we are able to understand how gas that is coming in and going out of the galaxy is linked with the properties of the galaxy itself. So this is possible because of the rich quality of data that is accessible to us. I don't have time to talk about this, but this is again evidence of cold accretion, cold mode accretion that is happening in our galaxies, which is one of the most dominant mechanisms by which galaxies acquire gas from the neighboring environment. There is a poster by our student Sumukha Bharadwaj, which is on display today and tomorrow. You are free to go out, free and check it out. Just want to end with these future directions. I am putting only future directions as relevant to quasar absorption line studies. Of course, there is a lot of progress that is happening in other domains as well in terms of observing these reservoirs of baryons. As far as future directions are concerned, I think a large galaxy redshift surveys, the current and upcoming large galaxy redshift surveys, they are going to provide highly complete large volume galaxy data, which is going to allow us to move from individual observer detections to statistical properties of galaxies, and this is going to be very important. And most exciting development is happening in the kind of synergy that is happening between simulations and observations. Rather than going after idealized simulations and predictions from them and comparing them with observations, now simulations are being prepared to match observations, similar kind of signal to noise, spectral resolution, survey volume, etc. Simulations are being done so that they produce outputs in terms of column density, covering fraction, equivalent, etc., which can be directly compared with observations, and that is going to be very useful in terms of interpreting the kind of things that we need to better understand how these baryons are positioned within the low redshift universe with respect to the large scale structure and with respect to individual galaxy systems. With this, I would like to end. Thank you.
Okay, questions? Yeah.
Thanks for that nice talk. I wanted to know this curve you showed of the deficit in the 16% baryon to matter density. What does that look like in filaments? Is that similar? Do we have sensitivity to probe that?
Right. So, the baryon to dark matter estimates for the filaments is not really known, because the filament observations of the baryons is incomplete unless you completely observe the WIM phase of it. For the photoionized Lyman alpha forest, there is a deficit, and that is because a large fraction of the baryons are present not in the 10 to the power 4 Kelvin plasma, but at much higher temperatures. So, for the intergalactic medium, this is not known until, this is not entirely known until all the phases of the IGM are properly measured.
Yeah, you mentioned that the metals generated in the galaxy tend to be thrown out in the galactic outflows, significant fraction of that. I was wondering what was the mechanism behind that? Why would the heavier metals end up being thrown out in the outflows?
Yeah, so for the dwarf galaxies, for the low mass galaxies, following an episode of star formation, there is going to be supernova events that are happening within a short span of time. And those individual supernova events or correlated supernova events, they are going to inject some amount of energy, momentum into the ISM, which is going to push the gas out. And this is going to be directional because perpendicular to the disk is where you have the path of least resistance. So that is going to create these bipolar outflows. That is the case for the low mass galaxies, displacement of metals. In the case of high mass galaxies, you will find that if I could flip quickly back to that. So in the case of high mass galaxies, you find that the amount of metals that are present inside the galaxies roughly matches with the amount of metals that are present outside. So that is primarily driven by AGNs. So AGNs are displacing these metals from the galaxy into the CGM environment, but a lot of these metals are retained within the galaxy because these are much deeper potential wells that these galaxies are resting in.
We can have one, yeah.
Actually, my question is about the overall framework, which your framework is adiabatic inflationary fluctuations.
Sorry, I'm not familiar with that.
No, I mean the fluctuations you are considering are adiabatic fluctuations where
Correct.
Photons and baryons fluctuate together.
Right.
People discuss isocurvature fluctuations, especially in the context of addressing lithium problem.
Okay.
That will change all of these. But do people, I mean, anybody
No, I
worries
am
about?
not aware of any of this, but I would like to learn more on this. I have not thought in this direction. Thank you.
Yeah, one more last questions there.
So again about this deficit, has there been any study of the baryon fraction in quasar host galaxies versus normal quiescent galaxies?
Yeah, so that's interesting. So I don't think there has been any major results on this, but there is work happening. People are trying to map out the amount of baryons which are present in the circumgalactic environments of quasars.
using quasars as background probes, and they are trying to see whether there is any major differences in this. One thing is for sure that the AGN activity is going to be going to create certainly a deficit, as we saw in this overall trend map. So galaxies which are hosting AGNs are going to have FB, this is baryon fraction, which is much less than the cosmological value. But in terms of direct observations, people are trying to do this, as far as I know.
Okay, thanks.
Okay, so let's thank the speaker once again. Next speaker is Shubhendu Rakshit, and he will be talking about weighing the monsters, supermassive black holes in AGN.
So very good morning, everyone. I am feeling a bit nostalgic here because about 15 years ago, I started my astrophysics journey from this place during my master. So coming back here after a long time, and all thanks to ASI for giving me this opportunity to talk about my research. So I will briefly talk about what I have been doing in recent years. So basically we are probing the supermassive black holes. These are black holes with masses millions to billion solar masses, and across the redshift range from local universe to redshift up to 8. So just to give you a brief introductions, so we know that there are billions of galaxies in the universe, and if you want to know the AGN fraction, is typically 10% of these galaxies host an AGN. So AGNs are powerful and more, it's a powerful and energetic process. It's a persistent object in the universe, emitting energy 10 to the power 42 to 47 arcs per second. They are powered by accreting black holes, supermassive ones, millions to billion solar masses. If you see the simple the hydrodynamic simulations, you see that when the object is accreting at a very low level, 10 to the power minus 6 times of Biddington ratio, then you can then you can see the galaxy as a normal one. It's a boring one. But if the same galaxy is accreting at a faster rate, 1% of the Eddington rate, then you see that AGNs appeared here. So Eddington ratio is the one of the key driver here for turning a normal galaxy to an AGN. And these things happens in the time scale of mega years with a duty cycle of 1 to 10%. And since these AGNs are varying over time, and you can see this variation across the wavelength range. For example, you look at the X-ray coming from corona, or you look at the UV and optical emission coming from the accretion disk, and you see the broad emission lines, which is the clouds. They respond to these radiations and they emit emission lines in the H beta or H alpha. You see also that dusty torus, which is obscuring the view, and they also emit in the infrared. Okay, so you can see across the wavelength range. Now we know that if you look at the mass density of the supermassive black holes, it's around 0.5 million solar masses per cubic megaparsec, and we know the galaxies are megaparsec apart, so every massive galaxy should have a supermassive black hole at the center. Okay, and this is true for normal galaxy, elliptical, spiral, both. And the galaxies which is sitting at the center, they influence the large scale host galaxy via feeding and feedback mechanism, and there is so called M sigma relations, which is very strong. This is true for inactive galaxies as well the reverberation mapped AGNs as well high and low mass AGNs. So if you plot the black hole masses as a function of redshift, what you see it's here. Okay. So this plot contains 0.5 million quasars in the SDSS survey. So here we used different methods to estimate the masses. So these are all single epoch black hole masses. I will come to this later. We use C4 emission lines for this high redshift one, redshift beyond 1.8. For the intermediate objects, we use MG2 lines, and for the low redshift objects, we use H beta line. So the most interesting point in this plot is that we see the presence of black holes with 10 billion solar mass. So look at the scale, it's a log, okay. So it's a billion solar mass black holes when the universe was very young at a redshift of 4. So this is from simple SDSS 0.5 million quasars. Now we know that so-called the JWST is actually coming and it's giving us very interesting results. So the little red dots, which is very popular name now. So this is the one of the famous discovery of JWST. You see the compact red point-like source which are spread across redshift more than 4, starting from 4 to 8. And these objects actually show a typical V-shaped profile, V-shaped ACD, where you have the obscured accretion disk may produce this decline part in the blue, while the rising part in the red could be due to the infrared emissions from the dusty torus. So, and if you zoom in this emission line, some of these objects and most of these objects actually emitting strong hydrogen lines. So, and this is an example of JWST uncover survey objects at AGN and located at redshift 8.5. And you see the broad emission lines presence H beta 3000 km per second. Okay, this is huge. If we plot all the JWST based black hole masses, so here is the black hole masses again and here is the redshift. Now the redshift is going from the backward this direction, so it's a back, the time is going closer to the early universe. So we are, let's say 0.5 giga-year when the universe was 0.5 gigayears old. We see that presence of massive black holes of 10 to 100 million solar masses. So how do such black hole can evolve? If you consider light seed of 100 solar masses, then you get this curve, this pattern. So they will not be able to explain the growth of these hypermassive black holes at this early universe. You need a heavier seed of the 100,000, 10,000 solar mass or so. Okay, so these objects also shows the high black hole to stellar mass ratio. So this is a 0.1 compared to the, let's say, local AGNs, which is in this these lines. So they are hosting overmassive black holes compared to the stellar masses itself. So the first question, the most interesting question that we are interested in and addressing, that what if these masses are wrong? What if these masses are overestimated? So let's look at how we can estimate these masses first. So for the local universe, you are very closer to the objects, so very low redshift 0.001. You can use the direct dynamical methods. So basically you can use stellar dynamics, you can observe the motion of the stars and resolve them, or you can use the gas dynamics, so ionized gas kinematics can stress the gravitational potential of the black hole, or you can use the mega measures. So all these methods has been applied from a long time and they are applicable to very low redshift. So if you want to measure the masses going from redshift more than 0.1 and above, so what you need to some kind of indirect methods. The reason is that to resolve the BLR or central engine of AGN especially, you need a micro-arcsecond resolution. So if you transfer this in the diameter of a telescope, so you need a telescope a few kilometer diameter. So this is not possible physically. So what we do is that we use the method that these objects are varying over time. So, and let's say the UV and optical photons that are coming from the central engine, they will come directly towards observer, but some of these the photons will be absorbed by the clouds sitting there and they will be re-emitted as a line emitting photon. And so you will see there is a delay between these two light travel time. So you monitor these objects photometrically, you see that the variations is there, and you monitor this as the emission line spectroscopically and you see the line variations. So then you can get the delay between these two light curve, and you can measure the distance of this line emitting region. Then you can use the simple virial relation, so you know that the distance r is there, and then you can measure the width of the emission lines from this profile, and then you get a mass. Okay, voila. But then there is a f factor sitting here, the scale factor, which is currently we think that this is a value of 5.5 because this matches M sigma relation of normal galaxy and AGN. However, in the early back in 2015 we showed that using a simple toy model, if your BLR geometry and kinematics is unknown, then you will heavily underestimate or overestimate the black hole masses. So, for example, here you see the scale factor is highly sensitive to the inclination. If you have a thin BLR kind of thin disk, then your F factor can go from 20 to 1, only change of inclination from 10 to 30 degree. But this is not the case if you have a thick BLR kind of spherical BLR type. So, so you need to basically study the F factor to estimate the black hole masses. One of the key achievements of this reverberation mapping method is to provide this single epoch scaling relation. So, BLR size is strongly correlated with the luminosity, and this relation is used to measure the black hole masses of all these objects that I showed, SDSS objects or JWST based measurements. So, here this correlation is very strong with 0.546 slope, and this is a classical relation in 2013. Then this is true for H beta, and the similar relation exists for MG2, but with a less number of objects because of the availability of unavailability of those observations. And we also have a C4 lines size luminosity relations. So these are helpful for single epoch mass measurements. But if you look at this 2013, we see this relation is getting outdated. Okay, so nowadays you have a more sophisticated telescope. I mean, there are a number of telescopes now, and there are a number of surveys going on in the spectroscopic domain. So, for example, SDSS reverberation mapping is one of the program. Then dark energy survey, OJDS, Australian Dark Energy Survey reverberation mapping program. Then SEMBH, another program, other thing. They are giving a new insight, and if you see this nice correlation now becoming ugly, and it's getting more and more deviating from these classical RL relations. So, we know that this relation is not only depends on the luminosity, but there is something else should be there. We also need to explore this low luminosity and high luminosity end, because this is where the JWST is coming into picture, and this low luminosity ends is completely unexplored. So, so what we did here, I will just give you a simple overview of this. We thought that in India we have the dot telescope, the 3.6 meter dot with the spectroscopic capability. So, why not to use the 3.6 meter dot and combine with 1.3 meter default? This is in our backyard, so you can use that. So, we continuously monitor this NGC 4395 for 2 consecutive nights with using the same two telescope. The problem with these objects NGC 4395, although this is the least luminous AGNs known to date, and you see the luminosity is 10 to the 40 arcs per second. So, it is a way down 3 order of magnitude below this normal classical type 1 AGNs. So, we use this intensive and these low luminosity AGNs, by the way, they do not vary much. So, there is less success rate to recover the lags and measure the black hole masses. So, we did some accurate flux calibrations and we we obtain about hundreds of spectrum every night. So, this is you see the variability that we see. This is the continuum variations in the photometry using 1.3 meter default combined with 3.6 meter dot, and here you see the emission lines how it's varying. So, emission lines we have multiple spectra, more than hundreds or so. So, you see the emission lines is varying very much, and it's following the continuum. So, we estimated the BLR size of these objects is 125 light minutes. This is a way down to compared to the other objects that I mentioned. It's days of the order of days. So, this object is hosting a intermediate mass black holes of the order of 20,000 solar masses, and we see these objects is accreting at a sub-Eddington limit of 6%. So, where is this objects is looking situated? So, this is the BLR size and luminosity relations. All these AGNs are located here, and our NGC 4395 is located here, and this is our another previous monitoring program why we did not get the successful lag. So, this is the observations that we found for NGC 4395. So, we are also pushing the RL relation to the high luminosity end, because for the high luminosity end, that is the domain where JWST is working, and but for this high luminosity region you need to have longer monitoring over the years, few let us say 5 to 10 years of monitoring, and that makes things complicated. But we did this pushing RL to the high luminosity end. So, this is for this purpose we collected hundreds of AGNs from Milliquezer's catalog, and then we monitored them continuously for 1 year, and we saw that only 32 AGNs are varying with a good chance of recovering lag. So we continued with our this monitoring program with 32 variable AGNs and keep on monitoring them. So for spectroscopy here we used a LEAK 3 meter telescope and MDM 2.4 meter telescope. For photometry we use small telescope like 1.3 meter LOAO MDM 2.4 and LCOGT. So the monitoring duration is about 6 years. So every week we observe for one night all these 32 objects whenever they are visible, and every 3 weeks we take one night for spectroscopy to observe all this. So this monitoring duration is 6 years, and after the 6 years of effort, what we are getting is this beautiful light curves here with 25 AGNs with reliable BLR size measurements and black hole mass measurements. So here you see the light curves are so varying so much, not only the continuum but also the emission lines, they are varying so much. And you can clearly see there is a lag between these two if you just look at your eyes, and this lag we applied very sophisticated methods to estimate them, but we see clear lags of all these objects. So where are our objects here? The high luminosity range. I am not showing the low luminosity part because the NGC43 is way down, it makes the plot complicated. So here the BLR size and luminosity relations, and the reds one is our this recent monitoring program. The LAM monitoring program observations are in the blue. Here the classical relations of Bench et al. 2013 was showing, I mean it is like this in the black one. And we see that our slope is much shallower compared to what was reported earlier. So, and this suggests that in the high luminosity end, the black hole masses, if you use the single relations, it's overestimated compared to what if you use the recent relation. So, so this is what we found. So, in not only in the H alpha, H beta, we also found the similar things in the H alpha reverberation mapping. And H beta and H alpha is closely following these relations with a similar lag. There could be another method, the way we can resolve the BLR and try to resolve the BLR. So this is called the spectrointerferometry. So it's similar to the radio interferometry, but in the optical domain. So this is a complicated process, how we combine the beams and so on. So, but the spectrointerferometry could be another route to measure the BLR size and resolve the broad line region. In 2015, we saw that how VLTI with 4 8-meter telescope can combine together, can be used to measure, to specially resolve the broad line region and estimate the black hole masses. That time there was only 3 8-meter telescope was there that can be combined together with the AMBER instrument that was proposed in our group. So we tried to observe the brightest quasars visible to us in the K band in 3C273, but we couldn't get any observations after trying three years. So later the gravity instrument came into play with a high sensitivity, combining all 4 8-meter telescope together with a maximum baseline of 120 meter, and then gravity collaboration we have successfully resolved for the first time 3C273. Here you see the typical S-type Keplerian kind of profile in the differential phase signature, and you clearly see the Paschen alpha emission line detections. So far we have successfully resolved the BLR structure using the spectrointerferometry also. So here is the broadline radius, BLR radius as a function of luminosity, and all these gravity observations are reported here, including redshift z equal to 2, these objects J0920. Here what we see a systematic deviation again that I reported in the reverberation mapping, and if we plot this our reverberation mapping observation on this interferometry, we see that they are clearly following the line here. Yeah, so this was the BLR based relations that we obtained so far in recently. But as we see here, some of the objects are still deviating. So we need to have not only the luminosity as a parameter, but we need to see that which are the other parameters of the AGNs can affect the BLR size measurements. So what I found is that Eddington ratio could be one of the main driver because it's changing the disk structure, becoming thin disk to thick disk. slim disk. So here you see that this relation becoming very strong if you include not only the luminosity but also Eddington ratio, where high accreting sources were deviating, but they are kind of coming closer together. And if we apply this relation, the best fit now this relation Eddington ratio dependency relations, we see that there is a overestimation of SDSS based masses also. So, and these deviations significantly correlated with the Eddington ratio. So, and these deviations of previous relations compared to these relations is 0.5 desk. So, you see this overestimation is significant for the high accreting sources mostly. So, now we can plot the same JWST diagram that I showed earlier here. The black hole masses as a function of redshift here, and you see these masses, since they are kind of reduced by a factor of few, we see that with a lower seed of 100 solar mass black holes accreting at the Eddington limit can still be able to explain majority of them. Even with a heavier seed with a duty cycle of 50% would be able to explain this kind of result. So we also, since we have very good quality data over the years, we could also probe what is going on in the center of the subparsec region of AGN. So we did some kind of dynamical modeling, and we see the different distribution of the XZ if you are looking the central engine in the XY edge on as well as face on for two different objects. So their geometry is completely different, even though they are AGNs, but geometry is completely different, and we see there are different kind of velocity structure here. So some are the Keplerian rotations, which is mostly dominated in this case, but we see still the inflow and outflow components present here. Yeah. And so then we further studied, so can the line profile, if you look at the shape of the emission line profile, they are different also. And so can the shape of the line profile tells us also how the black hole masses are affecting. So here what we plotted this FWHM, that's a line width versus second momentum of the line, and we see that this is also a function of Eddington ratio. So we see for high accreting sources we have a lot of turbulence effect and micro turbulence dominated. So there is a long wing component compared to the core one. So you see the Lorentzian profile compared to a simple Gaussian kind of profile. So this is one of the key that says that line profile can improve the single epoch black hole mass measurements, and you need to account for the Eddington ratio here. Then we look at the spectropolarimetry, because spectropolarimetry gives us an independent view. It allows us to indirectly probe through the scattered light the central engine. So our collaborator Kepati et al. Did a fantastic study of calculating taking the polarized spectra using VLT force instrument for several targets, several AGNs. So here what we see is that in general the width that is measured in the polarized spectra and the width that is measured in the total flux spectra, they are different, and this ratio actually decreases as a function of FWHM of the total flux spectra. So these actually suggest that you have a strong dependency of the inclination angle for this. But here look at the sum of the objects here, these are narrow line Seyfert-Wands type of objects, they are showing a relatively different view. So to further probe that, we actually use MMT S-pole instrument at 6.5 meter MMT telescope for spectropolarimetry. But in this particular object, which is a classical and the best known gamma ray emitting narrow line Seyfert-Wands, which is emitting gamma rays but hosting only million solar mass black holes. For this particular object, we don't see any difference in the flux and polarized spectra, and we, using a additive transfer Stokes modeling, we found that this geometry of this BLR is kind of thick, even though they are viewed as a face on. So beyond black hole masses, what would be the future directions and what we are doing now? We saw that reverberation mapping measured the linear size, interferometry measured the angular size. So if you can combine these two techniques using simple parallax method, which is known as the quasar parallax, you can measure the distance of these quasars, and then you can measure the H0, and you can probably address the Hubble tension. So here what you see that these two measurement, local early universe and late universe measurements are different, and we are trying to see if A0 independent A0 measurement can be helpful. This is the quasar parallax. You have interferometry that is giving you angular size, and the reverberation mapping is giving you the linear size, and you get the distance using this simple method. So this has been done for all these interferometric objects, about 5 of them. And we found a relatively H naught of 69 kilometer per second per megaparsec, which is a very promising. Obviously, you can see the error bars is very large actually. So, but we think that with the hundreds of AGN, let's say 100 AGNs, we can address this thing. So I already summarized this is my summary, but as you can see, the major things that I would like to highlight is that black hole masses are overestimated if you use the previous outdated relations, and the 2 to 4 meter telescope is very important in the era of JWST, because this actually tells you a different story. You can do a lot of monitoring and to understand these objects in detail. So moving forward, we have the black hole mapper program in SDSS 2.5, which will observe around 1000 quasars, the redshift range 1.1 to 4.5. But in the southern hemisphere, we will have the foremost 4 meter VISTA telescope, which will observe around 2500 objects using 2400 fibers actually. So its redshift range up to 2.5. And in the interferometric mode, we will have a 4 laser guided star for the 4 UTs, and then we could reach up to the K-band 13 magnitude and having hundreds of AGNs to do spectro-interferometry. But DOT and HCT will be ideal and crucial still for a large monitoring program for low luminosity AGNs, and we are still contributing with this. Thank you.
Such decent speaker is always good for the organizers. So every speaker is actually taking lesser and lesser and lesser time. So many more questions, yes.
Thanks, Suvendu. I wanted to ask about these estimates. You said that your these black hole masses were overestimated. So just by a factor 3 to 4, you are able to get the black hole seed down by such a large magnitude. So that was a little bit unclear to me.
Yeah, so we haven't included the H beta based masses. So this is the MG2 based masses. So you see that there is a decline, but the F factor is also reduced. So F factor usually use 5.5 for those masses. So if you let's say get F equal to 1, then it's a 5 times again reducing. So this combined effect of actually
combined gives you a factor 10 or something.
Yes.
Okay, thanks.
Hi, I have a question.
Yes.
So how are you measuring the Eddington ratio?
So Eddington ratio is simply here is just the volumetric luminosity by Eddington luminosity. So
no, my question is how are you estimating the volumetric luminosity? So you are using
it's just scaling, like this ACD of quasar, simple quasar.
So you are
ACD.
using a constant value for volumetric correction?
Yeah, for now it's a constant value, but we know that this could be also affected by quasars ACD type.
I mean, it also depends on the Eddington ratio.
Yes. So this is very complicated because you cannot have the entire broadband ACD to estimate individual objects of 0.5 million or so. Even though so there is some effects. I mean, we see that there could be uncertainty of 20% or so in the Richard paper. These are it.
Hi, Shubhendu.
Yes.
Thanks for the talk. A very basic question about your luminosity versus your BLR size plot that you made. Would it not depend on the luminosity of the black hole at that time? I mean, what is the variability in that 5100 angstrom itself?
Yeah, but 51 luminosity of that time, you mean? So we are taking a snapshot and we think that it's the average luminosity you can put, because that scaling is, it's not much. I mean, its variation may be 20% or 30%. It's not like Blazar kind of sources that vary significantly. Okay, so we take the average, we construct a mean spectra for let's say hundreds of spectra you obtain throughout the monitoring, and mean spectra from the mean luminosity we are putting in.
How long do you take average of?
So it's like for this long monitoring, the high luminosity agents, we had 6 years of monitoring.
I see.
So within 6 years we recovered let's say 50 spectra, we took a mean of this spectra and get this luminosity.
I see, but what happens when the variation is actually longer, like hundreds of years, and suddenly you are in a situation?
How you will get these observations of hundreds of years?
Yeah, that's the point. Like then you're
so then that cases we see that, let's say I showed the simulations also. Let's say in that case the agents can be, if you consider thousands of years, then you cannot apply the same method, right? So it's but we see the these gas motions are virialized. So we see that there is a inverse correlation with the luminosity and the virialized the velocity of the gases there. So L proportional to L v square to the power -2. So
thank you.
There's another one. Yeah, another.
So yeah, nice talk, Suvendu. So I was wondering about this F factor you are using in this RM method. So whether it is the value of F5.5 is valid at very high redshift as well, or because this is constrained by the low redshift?
Yeah, so far we couldn't get this this study because our sample is limited up to, let's say, all this reverberation mapping sample is limited up to 0.6 or 7. Mainly the observation due to the observation, but you see the F factor is has a significant. I mean the values are kind of, let me see. So there's no. So it varies a lot, but not, let's say, between 10 to 1. So there's a variations, and for 38 AGNs we have estimated this F by modeling those the spectra in all the spectra throughout the monitoring. So it's a geometrical. So there is the vector, but we haven't. I mean the error bars are so large that you cannot study this currently.
If there are no more, one more, yeah, okay, because he finished almost 4.5 minutes.
Okay, so this Eddington ratio that is turned out to be crucial, but that also depends on the mass.
Yes, but we independently checked with the Fe2 strength. That is independent of mass. Fe2 strength is basically the strength of the Fe iron templates with respect to the H beta emission lines. So that is independent of the mass, but we see that there is a strong correlation with the Fe2 strength and the Eddington ratio. So that is an indirect way to confirm. Because we don't have the Eddington ratio estimates through the SCD fittings or other broadband SCD. So.
Okay, thank you.
If there are no more questions, one more, okay.
So a very naive question. So now with this measurement, from the classical or traditional relation that you have, is the higher end is modifying as well as lower end, or what is the current?
Lower end we only have a single object, NGC 4395. This is 3 order below. So if you look at this relation, so with this one single object we cannot claim anything. So we just didn't consider these objects for any fitting, because we need to have a multiple objects, but we don't have any such low luminosity AGNs that we can monitor, because they do not vary also. Even we tried for longer time for other targets, known targets, but they don't vary. So if they don't vary, then these methods cannot be applied.
And high end?
High, it's modifying, right? In
Yeah,
the high luminosity is becoming shallower compared to the previous one.
No, so I agree, but what I want to know is like, so you have data from, I think, the one measurement that you have connected and the previous ones.
Yes.
So it's a total fit, or the newer ones, the data only that you have?
So no, so it's total fit.
Okay.
Total fit is slightly shallower with a slope of 0.4 compared to the 0.54 that was known.
Okay.
And then we are also considering the Eddington ratio dependency to reduce the scatter. Then it's actually improving a lot for all these SDSs also.
Okay, let's thank the speaker once again. Next speaker is Mayuri Rao, and she would be speaking about global cosmological signal detection experiments at radio frequencies.
Hi, am I audible? Okay. Good morning, everyone. I'd like to thank the Scientific Organizing Committee for giving me this opportunity. So I'm going to be talking to you about a few experiments that we've been doing at our lab at RRI that are trying to detect global cosmological signals at radio frequencies. So very quickly, let me break this down for you right at the beginning. When I say global, I mean these are signals that come to us potentially from all directions in the sky. You can think of this as the radiation we see from the cosmic microwave background that comes to you from all over. And of course, these are cosmological signals, as in the sense that they come to us from high redshifts, we see them at radio frequencies. Very quickly, this is the group at RRI. We call ourselves the CMB Spectral Distortion Lab, and special thanks to funding agencies that have supported some of this work, including DST, SCRB Core Research Grant, and ISRO. So we have seen this picture a few times already in this conference, but I have to show this again, so I apologize. So on the left is when our clock starts ticking. We call this popularly as the Big Bang, or the point when the universe starts. And we know that within the first few minutes, all the baryonic matter in the universe, matter that you and I are made of, exists in the form of plasma, so protons, electrons, helium nuclei. And this coexists with the radiation that is emitted in the energetic early universe. Gradually though, when the universe is typically about hundreds of thousands of years young, the protons and electrons combine to form the very first atoms. And the radiation from the early universe is free to escape towards us, and today we see this as the cosmic microwave background. So this process of the formation of the first atoms is expected to add photons to the CMB spectrum, and that is the first global cosmological signal of interest to us. That is the first pink box on the left. Eventually, this neutral gas in the universe starts falling into dark matter potential wells and starts forming the very first sources of radiation. So basically the first stars and galaxies in the universe. And this change in the 21 centimeter emission from the hydrogen gas is a tracer of the formation of the very first stars and galaxies. So that brings us to the second global cosmological signal we are interested in, which traces the first stars and galaxies. That is the middle pink box. And of course, we are here today in the local universe looking out into the sky with our telescopes, observing these very early universe cosmological signals through radiation from our own galaxy. But as much as we try to understand radio emission from our galaxy, the diffuse radio emission, so emission from our galaxy at very large scales, is not as well understood as one would like. And this is what I call the third global signal, and there are some missing pieces of the puzzle here that I will touch upon. Okay. So when you go up and you think about the cosmic microwave background, you think of images like this, which is the anisotropy or the fluctuations in the temperature of the cosmic microwave background. And clearly, since its initial anisotropy measurements with the COBE in 1992, we have made tremendous progress in mapping the spatial anisotropies in the cosmic microwave background. However, the same cannot be said of the spectrum of the cosmic microwave background. So this is the plot of intensity versus frequency of the CMB spectrum, and you can see that it follows the curve of a black body nearly perfectly. I think this is to date the most perfect natural black body, and the error bars here have been blown up by 400 times just so that we can see them on this plot. And this measurement of the anisotropy and spectrum was awarded the 2006 Nobel Physics. However, we do expect from standard cosmology that the spectrum of the CMB is not a perfect black body. We do expect standard processes that inject energy into the CMB spectrum to deviate the CMB spectrum from that of a black body. There are upper limits on these deviations. Some of them, the more popular ones that are studied, are called the mu and y distortions. And these have an upper limit of the order of 10 raised to minus 5. So rephrasing this, the CMB spectrum has been measured to be black body to 1 part per 100,000. But Standard physics, standard cosmology predicts that the deviations that we expect to see are maybe just at a level below. So 10 raised to minus 6, 10 raised to minus 8. At these levels, if we are able to make precise measurement of the CMB black body, they will deviate from what we have been seeing so far. So here are some standard deviations that we expect, namely mu, intermediate and y as you go from early universe towards us. But the one that we are interested in our lab, like I mentioned, comes from the formation of the first atoms over the period of epoch of recombination. So why is this interesting? First of all, it's a probe of the early universe. It helps us trace as a function of time the thermal and ionization history of the universe going beyond the surface of last scattering. And if you go into more theoretical details, you will find that if you are able to measure these CMB spectral distortions, you are able to get clues about properties of dark matter, energy injection processes in the early universe from exotic physics, as well as you understand structure formation through the Sunyaev-Zeldovich effect. And for my interest in the study of these recombination lines, we are able to experimentally measure pre-stellar helium abundance at cosmological timelines. So this is a quick picture of all the efforts that have been attempted or being attempted post-COBE. This was now 25 years ago. And other than ARCADE and another experiment called TRIS, which is not shown here, none of this have yet flown. Many of these are space-based missions. This was a picture from the fossil collaboration in Europe, and happy to note that our experiment Apsara is on here. So let me tell you a bit more about Apsara. So Apsara is an upcoming experiment that we are working on at RRI in the S band, operating between 2 to 4 gigahertz. What we are trying to detect is the photons that are emitted into the CMB when the first atoms form. Very simply thinking about this, when you have electrons that are captured by a nucleus, say a proton, and the electron trickles down from higher to lower energy levels, clearly you expect photons to get emitted. These additive photons to the CMB path are expected to be at a level of 1 part per billion, and these again are an inevitable prediction of standard cosmology. But before you try to build an experiment, let's see what the challenges are. So on the left is the cosmological signal we are trying to find. That signal is already faint because of baryon to photon ratio being very skewed. This signal comes to us through extragalactic point sources, our own very bright galactic radio emission, and of course we measure this in the presence of very strong contaminants such as the terrestrial radio frequency interference before it reaches our telescope. So working our way bottom up, we first try to address the most fundamental challenge to this experiment, which is understanding the contribution of galactic radio emission at large scales to a signal detection experiment. Okay, so this is a picture of the radio sky at 408 megahertz, very famous Haslam map, and you see there are very interesting large scale features, but more notably this is extremely bright and it is spatially varying. So all of these features will show up in our measurement set when you stick an antenna on the sky. The radio emission of our galaxy at large scale has measurement errors of 1 to 10%, higher at lower frequencies and little lower at high frequencies. So we do not really have a complete picture of the emission from our galaxy, including effects of the interstellar medium at large scales. So first we went ahead and we built a model of the radio emission from our galaxy. We call our model GMOS. And GMOS essentially uses all sky surveys that have absolute temperature calibration on them, because that is critical for this kind of an experiment. And at every single pixel, we effectively interpolate between these radio frequencies as a function of direction using real physics we know that exists in our galaxy. So we describe our model with some handful of parameters, including synchrotron emission with the possibility of a spectral break or multiple source populations. We put in free emission, absorption, and while this serves for us for this experiment as a very nice model of the foregrounds to the cosmological signal, This has been a workhorse for us in terms of also trying to understand processes of the ISM itself. So now let's look at what this foreground actually looks like if I make a measurement. So if I take an antenna and put it on the sky and I make a measurement, the way these foregrounds translate into a data set is shown on top, where you have temperature versus frequency, and that's our effective measurement. I'd like to remind you that even though we think of synchrotron emission as a power law, when you have multiple power laws in an antenna beam, the summation of these is no longer described mathematically by a power law. So you have to figure out a way to mathematically describe this integrated galactic radio emission. And for that, we've come up with some algorithms in the lab, notably something called maximally smooth functions, which has now been adopted globally for many experiments that are trying to look at other 21 centimeter signals. I'll come to that later. But effectively, what this function does is it's able to describe the smooth component in the data, which in our case is the galactic foreground. Now, if I add the CMB spectral distortion signal to this data set and I describe this with a smooth function, I see the residual, and this is the signal I'm trying to detect. We have found from feasibility studies that to maximize signal to noise ratio, the frequency range you want to operate such an experiment from the ground is somewhere between 2 to 6 gigahertz. So I have zoomed in on that frequency range. So over 2 to 6 gigahertz, you see that you're able to recover the signal from a simulated data set that include foregrounds which are about 1 billion times stronger. And the signal looks very interesting. It looks like some wiggly sine wave shape, and this is what we have to detect. But I'd like to remind you that the amplitude of the signal is the order of tens of nanokelvin. It's an extremely faint signal. So our feasibility study again shows that you need an array of antennas with absolute temperature calibration. We need about 128 antennas with cooled radio receivers observing the sky for about 1 year to be able to make this signal detection. And this signal has never been detected before. So we go about this experiment by building the first such element. So an element would look very simple. It will have an antenna with some electronics, and that is connected to a digital receiver, and then that is connected again to your computer and you analyze the data. So this is what it looks like today in parts in our lab. On the left is the antenna. So I'll talk about each of these quickly in the coming few slides. We have custom designed antennas with prioritizing two aspects. First of all, we know we want to make an array of this experiment. So you want your antenna to be scalable. So a planar antenna is perfect for this. You can print out many of these extremely identical and make an array very quickly. And the second is that you want your antenna to be able to follow certain ground rules, such as you want to be able to separate your signal from the foreground effectively. So you do not want to violate that cardinal rule, and you don't want to mix up your the shape you see in your signal, and you do not want to introduce artificial shapes in your data set. So this antenna does that. Then we come to our electronics. We have cryogenic RF electronics that are cooled to 77 Kelvin for now. We plan to upgrade to 4 Kelvin very soon. And we also have some room temperature electronics. And finally, we have a digital receiver that digitizes and converts the data set into a spectrum. With the first element, we are not aiming for a 1 part per billion detection, but we are trying to go after two very important problems. On the left is the temperature measurement of the CMB at low frequencies. So while I showed you this very beautiful black body curve from FIRAS in a previous slide, those are all at frequencies of hundreds of gigahertz. At low frequencies where we are operating our experiment, the error bar on the 3 Kelvin CMB is actually as large as 1 Kelvin. And there could be a lot of interesting physics sitting in those error bars. So we want to constrain the temperature of the CMB to 1 part per 10,000, effectively improving the current best temperature measurement of the CMB at these frequencies. Also, coming to the other global signal I was talking to you about, there have been reports of a detection of what is called as an excess radio background by a couple of experiments, namely RK2 and the LWA. And what this tells us is that there could be a source of radio emission, either local or cosmological, coming to us from all over that is unaccounted for, and this is a big problem. We would like to know what sources of radiation we are picking up in our antenna, and this has extremely strong implications including things like annihilating dark matter, so fundamental physics can be probed. So it is important we address whether or not this excess radio background is real, and if so, what could cause it. So Narendra here has been looking at this problem specifically. So using models of the radio sky and GMOS itself, he has been trying to go after seeing whether this excess radio background was an artifact of data analysis and interpretation from the previous experiments, or whether if it is real, what is the right experimental strategy to go ahead and make a signal detection. So we have been making custom antennas, so clearly our antenna is not a standard dipole or a parabola, and like I said, the emphasis has been on scalability and to increase your prospects of signal detection. You do not want your antenna to introduce artifacts in your data that can confuse the signal detection. This antenna operates over 2 to 4 gigahertz, and we have started getting into very interesting domains of using machine learning algorithms to improve our antenna design performance. So we actually look at the currents on our antenna and tweak our antenna such that its performance improves, and this is work that should be out shortly in IEEE. This is our radiometer architecture. It's a very standard Dickey switching radiometer. So basically you have an antenna and you calibrate it against a hot and a cold load. The hot and cold load, in this case we also have the advantage of using physical loads because we have a cryocooler. We also have redundancy built into this architecture where we have artificial noise injection using an electronic noise source, and then that goes on. This is the cryogenic setup. I'm dedicating a whole slide to this because this is a significant part of the kind of work that we are doing in our lab right now. So this is a Stirling based cooler that we have pumped down to high vacuum, 10 raised to minus 6 millibar, and all our RF electronics sits inside this. And this is important because it reduces the noise contribution from the receiver in your data. Otherwise, we are going to have to conduct these experiments for beyond human timescales to make a signal detection. And this is the digital part of the data, the experiment. I will not be emphasizing on this because Akshaya has a talk on this later in the afternoon in the instrumentation panel session. I encourage you to go attend. Quick summary is that we have now moved to the latest generation of FPGA platforms, what is called as RF system on chip, and she's been doing some really nice work with our scientists. We've gone out to different sites to find the suitable site to deploy such an experiment, because clearly if you go to a site that has high radio frequency interference, we are not going to make a signal detection. In this effort, we've gone across various parts of the country, and our colleague Girish has also gone to the Himadri Arctic station a couple of winters ago and made this measurement. And we find that our biggest sources of RFI are satellite downlinks and 4G, 5G communication. So it is getting a little more difficult to find radio quiet sites anywhere in the world. Another important contributor to noise in our data comes from the atmosphere itself, because atmosphere has water vapor and that can effectively change your atmospheric transmittance. Typically this is a problem for submillimeter experiments, and Bhashwati talked about this in her talk earlier this week. But even for our experiment at few gigahertz, atmosphere can contribute a few Kelvin to the total noise. So that's a few Kelvin, and we are trying to do a nanokelvin detection. So it is something we have to account for. And in that effort, my student Tanmay Singh, who's now a grad student at ASU, looked at what is called reanalysis data sets, and we mapped out the entire Ladakh and Spiti region to see if there are suitable sites purely from precipitable water vapor point of view. And we find that overall Ladakh is extremely promising and underutilized, and this will also feed into Indian efforts for submillimeter astronomy. To make measurements of the water vapor, we have gone out and deployed GNSS based receiving systems at IAO Hanle a couple of summers ago, and we are looking at the data now. And I'd like to thank IIA, IAO and the whole team that helped us set this up. So I've gone on for a while about this specific spectral distortion and experiment. I'll take a quick recap here. There are very interesting physics hidden in cosmological spectral distortions that comes to us from all over the sky. These have never been detected, but it is very important to go after them because they have largely been kind of ignored in favor of anisotropy measurements. We are building Apsara from RRI to go after the cosmological distortion from recombination or the formation of the first atoms. Our first goal is to measure the CMB temperature to 1 part per 10,000 and to give the final word on the existence of the excess radio background. In the next 5 minutes, I'll quickly go over another experimental effort which is an important part of our group, which is to detect the global signal from the very first stars and galaxies in the universe. As I mentioned, the universe is filled with neutral hydrogen after recombination, but at some point the very first stars and galaxies switch on. This effectively changes the 21 centimeter content in the universe because neutral hydrogen gradually disappears because new sources form and the hydrogen is reionized. Specifically, we are looking at a few periods from the ground, namely the cosmic dawn, which is the deep trough there at around 70 megahertz, and the epoch of reionization, which is around 100 megahertz. Again, x-axis is frequency in about tens to hundreds of megahertz. Here, the dynamic range of the problem is 1 part per million because galaxy can be about 1 million times brighter than the signal we are looking for. In 2018, an experiment called EDGES from the US reported the detection of an extremely anomalous signal from this cosmic dawn, which is showed in the black dashed line. However, our group has since then refuted this measurement with the SARAS-3 measurement. But one of the reasons why it has been an extremely challenging problem to detect this global signal from the cosmic dawn is because of the operating environment of where we deploy our telescopes. So 3 notable challenges specific to the environment are radio frequency interference that I discussed. There are also ionospheric effects where the ionosphere can reflect, refract and absorb radiation. And less talked about is the fact that when you design an antenna very well in a solver or measure it in an anechoic chamber and you place it in a real operating environment such as a field, the antenna properties change non-trivially to, and again we are trying to do this at 1 part per million, but these are things that are extremely hard to model in any solvers. So the ideal environment to operate such an experiment would be the far side of the moon, because the far side of the moon has been known to be radio quiet from previous measurements. So keeping this in mind, we have proposed an experiment called Pratush to ISRO. This is a quick summary of Pratush. Pratush will operate over 55 to 110 megahertz, focusing on the signal from the cosmic dawn. We expect to fly in 2 phases, one as a precursor phase around Earth and another in lunar orbit. And we have got funding from ISRO to develop the laboratory model. So this is what Pratush would look like. It would be a dedicated craft orbiting the moon, making scientific measurements when it's on the lunar far side and in the shadow of the Earth and the Sun, effectively blocking RFI. It will be an orbiter to minimize any coupling effects of the antenna to its environment, and there is no ionosphere to speak of around the moon. And the reason why we are focusing on the cosmic dawn, even though in principle these are frequencies accessible on Earth, is because this is where the parameter space is the most open. This is where we will effectively nail down the problem of Lyman alpha transfer, which has been very hard to solve in computation. And the signal to noise ratio in this band is much higher than the other bands that I had shown you. And there is no other complementary probe we can use, such as Lyman alpha or JWST. So this is the right frequency range for the highest scientific return. So this is why we are focusing on this band. This is what Pratyush is envisioned to look like. It's clearly a very interesting looking telescope. The grey structure is the antenna which sits on the electronics, and on the right is what it looks like in our lab today. We have been routinely running measurements of our receiver to see if our receiver calibration scheme is alright, and very happy to say that at least in the lab our receiver has shown that it is sensitive to be able to detect the signal we are going after. It has noise of few millikelvin, and the signal we are trying to detect is tens if not hundreds of millikelvin. So we are good to go in terms of a radiometer architecture. And Narendra has a poster on this that he'll be talking about, so please go check it out. And because lunar launches are few and far in between, we are also doing a small mini Pratyush called Pratyush 0 that Bharat spoke about yesterday in his talk. This is envisioned to be an orbiter that will do two things. First of all, it will map radio frequency interference. Secondly, it will be able to make measurements of this average or global signal from our galaxy, and this is the current status, and this we hope to have a quicker launch sometime soon. The far side of the moon is going to get very busy. We are not the only ones trying to do this. There are experiments from around the world that we are in competition with, and whoever gets to go first with a good experiment effectively gets the larger slice of the pie. So hopefully we are also in contention because at this stage we are neck and neck with the best in the world, and hopefully India will make the discovery. So I will stop here, and this is my summary slide. Hopefully in these 25 minutes I've convinced you that there is a lot of interesting physics in global cosmological signals. Signals from the first atoms, it's a 1 part per billion problem, will tell us about energy injection processes in the early universe. Signals from the first stars and galaxies is a 1 part per million problem, will answer the open problem in cosmology about how the first stars formed, what they look like. Signals from unknown radio sources is this excess radio background that Apsara will go after first. We don't know if it is real, and if it is, it's very exciting because we really have no explanation for it. And we are trying to understand our own galactic emission at large scales. And all of this requires extremely high precision calibration, accurate electronics, data processing methods, mathematical techniques, and characterization of the environment where the telescope operates. So I'll stop here and take questions. Thank you.
Questions? Prabha.
Very nice talk, Mayuri. So I had a question about the maximal function that you do for the foreground subtraction. So the question was that that is basically for the global signal, right?
Yes, so this is mostly to describe the foreground, the galactic component of the data.
So when you do the, when you describe the function, shouldn't it depend on when you, when you measure the global signal, you are not going to actually do the entire sky, but it will only be some fraction of the sky. So would it not depend on which fraction of the sky you're looking at, because the foreground is in principle fluctuating across the sky?
Yes, thanks Prabha. So we have looked at this. So we put in GMOS as our input sky model. So we kind of trust the physics that we put in. And when we convolve an antenna beam to different patches of the sky, effectively the fit parameters change. We do find, however, that be it looking towards the galactic plane or off the galactic plane, the function remains smooth. It is just that you need more, it gets a little harder to solve for the smooth function towards galactic plane because it's a little messy. But irrespective, it is smooth to the error bars in the input maps.
Okay. Yeah. Okay. Yeah. Thanks.
Thanks, Mayuri, for this very nice and clear talk. I again have the same question like Prabha about this theoretical model that you have for this galactic foreground. So can you please go to that plot? I just wanted to know, there were several plots. So
I'm coming. Thank you.
This one.
Yeah, this one?
Next one. Yes. So what are these lines corresponds to in different lines? In
Yeah,
this
so
plot?
this is exactly what Pravas said. This is a function of LST. So we have some different time observations of the foreground sky. And we see that when the galaxy is in our beam, in our simulated beam, you see the blue curve. When we are looking completely away, it is the red curve. So
Oh.
we do take this into account in our modeling.
Okay, okay. And another question, so which I think I'm a bit curious about, is that CMB is a microkelvin signal,
Yes.
right? And what you are after is a nanokelvin signal.
Yes.
So how hopeful you are getting it detected from ground-based experiments than space-based experiments?
So I'm hopeful in the sense that this is the signal prediction is extremely clear. So that has been the driving factor in us designing our experiment, because unlike, for example, the signal from the cosmic dawn, which is very messy and you don't know exactly what you're looking for, in this case we know exactly what we're looking for. So we can really throw all our techniques possible to at least make a detection, if not a perfect measurement. Statistical detection is something we can make, and I didn't show that work here, but all these things have shown assumed a perfect antenna or a perfect experiment. But we have done feasibility studies with even an imperfect antenna, and we think statistically we can still detect it just because we know what we're looking for very well. Thanks.
Yeah, Ajit.
Okay, let me ask you a very provocative question.
Yes.
Now, people when talk about Hawking radiation from black holes, they immediately tell you that stellar black holes are useless because they emit in nanokelvin.
Yeah.
Now you are talking about nanokelvin, so I'm really excited.
Yes.
Do you have any plan of detecting those?
I have been told by theorists, let me start that way, that we do expect signatures of primordial black hole evaporation to show up as a CMB spectral distortion.
No, I'm talking about stellar black hole. Primordial, of course.
I'm not sure, okay, unless if it is like a background per se and we expect it all over, I don't think we will pick it up in our kind of experiment at least. But because we are not really tuned to...
Maybe because it's a thermal radiation. So the Hawking radiation is a thermal radiation, so it might get lost in other thermal radiation. I don't know.
Yeah. So if, but just kind of reframing, if we go down to nanokelvin sensitivity, we will have to account for every single contribution we see in our beam. Maybe we'll see it. I don't know.
If there are no more questions, can you go ahead, please?
So it looks like excellent work is going on in your lab. I'm just curious about this technology development thing. So you are spending a lot of effort in designing the perfect antenna. Now, is it possible that somewhere else in the world, some other people have designed this for some other purpose, which sort of suits your purpose? Is that kind of thing possible, or that is something that you think about?
Yeah, I mean, we of course are doing our extensive literature survey and talking to different groups, even from other domains who don't do astrophysics, for example. We have a very unique challenge that we want a wideband antenna, but most wideband traditional antennas are what we call well matched, in the sense their response has resonances which makes them well matched and hence they are wideband. We go the complete opposite direction. We make our antenna intentionally bad so that we have a stable beam over the full band. So the short answer is that we think it's unlikely people want to design a bad antenna like us because our requirement is so weird.
Thank you.
Okay. I think we have to stop because organizers are restricting it. Okay. So, yeah, okay. I'm giving time people to ask questions. And the speakers were so generous. Okay. Anyway, so let's thank all the speakers of this session. Excellent talks. And I think there is an announcement from the organizers.
So we have been getting queries regarding participation certificate. So the participation certificate will be available in your profile, the ASI 2026 account profile. After the maybe within few days after the meeting is over. Okay, so this is one thing, and of course again I will request those who have got travel grants, please do submit your TA forms with hard copies of your tickets etc. to the ASI office. Yeah, thank you.